Hello everybody, dear students, I welcome you today to this lecture. It is the Green's theorem in the planes. You know, this Green's theorem in planes is mentioned in different syllabuses. In vector calculus, vector integration, it is also expressed there. In different courses, this is in Green's theorem, and it is very important theorem. With the help of this, we have the Stokes theorem, generalization of this Green's theorem. We have this Gauss divergence theorem after this. That also is the consequence of this Green's theorem. Well, actually, what this Green's theorem is, this Green's theorem gives us the relation. It develops a relation between the line integral and the surface integral. Very important when you want to express the line integral in terms of surface integral or surface integral in terms of line integral. This is the Green's theorem. But before we start the Green's theorem, it is statement and proof. Today we are going to do statement and proof. Before we give it a statement and proof, we have some outlines. That is something that is involved in the statement, that is involved in its proof, that I say it is the outline of the proof. First, I want to discuss with you the outline of the proof. Let us have this outline of the proof. I will give you some outlines. This is I name it outline of statement or proof of this theorem. After this, I will state and prove this Green's theorem for you so that you will fully understand. First, I want to define what we mean by open and closed regions. Open and closed regions. Simply, you have also done it, but I want to just to recap or recapitulate you. I want to just take something from your unconscious memory to the conscious one. I want to take it to higher level. Open and closed regions. We say a region is said to be open if it consists entirely of its interior points. It only consists its interior points, whereas it is said to be closed region. It is said to be closed region if it contains all its boundary points. When it contains all its boundary points also are contained in the region, interior boundary, then we say it is a closed region. It is known as closed region. So this is what we mean by the open and closed regions. I think you have understood this. Second thing I want to share here, it is what we mean by simple closed curve. Simple closed curve. You see, if you take a curve, this, say it is A to B, it is open. When you close it like this, here this point moves here, here you can say A is equal to B. We say it is simple closed. You may have like this, simple closed. But in some cases you have also closed curve like this. It gets intersected at one point. So we say this curve is closed, but it is not simple closed curve. It is not simple closed curve. Number 3, we define now with the help of this what we mean by third point I want to share with you. Simply connected region. Actually, in higher studies, in some physics studies, we have the simply connected domain and simply connected regions. It is a complete chapter there. It is a vast chapter. What we have properties we derive from simply connected regions. I want to here simply give you the definition and idea what we mean by simply connected region. We define it as simply a simple connected domain or region is a connected path, region or domain such that we can continuously shrink. It is very important. We can continuously shrink a simple closed curve, into a point. That is, when you have a simple closed curve like this, when in a domain or region you can shrink this, you can reduce this into a point, then it is known as simply connected into a point. Now in two-dimensional region or domain, the simple connected domain is without holes in it. It is without holes. Means if you have a curve like this, look here. If you have a curve like this, this is curve A. It is simply connected. When we can reduce it into a point, this is simply connected. If you have a curve like this, this is not. It is not simply connected because you have holes, you have another curve lying in between this. This is a little bit idea. I am not giving it because there are the different forms of this simply connected region. I am not just touching those. I want to just what we have to do in Green's theorem, what the statement says. Next, I want to give you some idea how we draw the graphs of the inequalities and the curve under the inequalities. You look here. You have inequalities. It is, suppose we have the region. If we consider the region bounded by A less or equal to X less or equal to B, and y is greater or equal to f1x less or equal to f2x. Suppose this is the region. This is a region. Simply connected region. I have given you what we mean by simply connected region. Suppose this is the region. You want to draw its graph. How will you go? You see, just look. This is your xy plane. When you take x is equal to 1, this is your x1. Assuming that this is x1. This is your x1. xa, sorry. This is x, your x is equal to a greater or equal. Greater goes this way. Then this is xb. This is your x is equal to b. This line, x is equal to b. You know, when you draw the graph of x is equal to alpha, it is a line parallel to y-axis at a distance a from the origin. You know it. It is a from the origin, and this is what? B from the origin. You know it. When you draw the graph, when you have x greater or equal to a is this part, away from the y. And when you have x less or equal to b, you have x less or equal to b here, this is this part. Do you follow me? That means your region, your curve, this curve lies between what? This part and this part. You may go this way. Suppose I am assuming this is your curve. Just to look. This is my curve. I will go this way, assuming this is my. This is your y equal to f1x. This is y equal to f2x. And this will be your region. I am just giving you the notion how to draw the closure path. This will be your region R. This is your region R. This is the graph of this inequality. When your x is greater or equal to a, less or equal to b, these are the equations of the curve. This is y. Why I write this up below because this is y equal to this. Your y is greater or equal to f1x, less or equal to f2x. So f2x will be upper side, f1x is lower side. When your y is greater, it goes upward, region is upward. When here y is less than f2, it goes lowerward. So this goes forwards the closed region. This is the graph of this, how we draw the graph of this. Now the question is, when you take the positive path or closed path, you always take the direction of counterclockwise. Why it is counterclockwise? When we talk of positive path, whenever you make a round along this pond, when you walk on the pond boundary, it should always lie on your left. You see, you walk here this way, this lies on your left. This is the positive path. Okay, positive path, in positive path, closed path, it should always lie on your left when you walk on the boundary. When you walk on the boundary, it should lie on the left. You know, I want to share with you here a very important thing. When you go to Makkah, the holy place, there we have the Kaaba. When you make a round along the Kaaba, your consciousness may say that we should keep right shoulder towards the Kaaba and move. If you go that way, your round is not complete. No, your round is not complete. You do what there? You take the left shoulder direct in the direction of the Kaaba, and you move left side. That is, when you make the round, your left shoulder should always lie along the Kaaba. That is the positive path. That is the closed path. Otherwise, if you make the round in a direction when your right shoulder is towards the Kaaba, that is not your count will not be completed. No doubt the Islamic scholars have some other this reason for this. They have the Islamic reason, this on the basis of the Islam. But this scientifically we say that when we move, this should lie on your left side. This is the positive path. Whenever you move along a curve, along a pond, along this, if you want the positive, region should lie on your left. This is the positive path. We take this positive path this way. I think you have understood this, how we draw these figures. Now let us go to the statement and proof of this green value theorem. Theorem. Green is the theorem. Green is theorem. It is proof. You will enjoy it is proof and statement. Now it is clear to you. You see how we go. Let us have the statement of the theorem. This is the statement. Statement of the theorem. Let me save your time. I will write the statement of this theorem. Okay, students, I have just given the statement and vis-a-vis the this diagram of this figure, region, that we will consider the region, so that the time is saved for you. I will read the statement here. What is the statement of this? The statement is, suppose R is a closed region. R is any closed region which is simply connected region. I have defined what we mean by simply connected, so there is no doubt about it. In the xy plane, because it is the Green's theorem in the plane, in the xy plane, bounded by a simple closed curve C. It is bounded by the simple closed curve C. This is the region R, bounded by simple closed curve C. I have also drawn the figure here. And M and N, these are the, M is a function of xy, N is also some function of xy, such that this M and N together with it is partial derivatives. Partial derivative of M with respect to y, partial derivative of n with respect to x. We need partial derivative of m with respect to y, partial derivative of n with respect to x, are continuous in the region R. These must be continuous. Continuity, you know, I have not to give it is definition. Continuity means it is defined each at every point, and continuous means there are no gaps, there are no holes, there are no breaks. You know it. Then the line integral. I have already told you that this Green's theorem is a very important result which gives us the relation between the line integral and the surface integral. And the line integral of the closed curve C, m dx plus n dy, m dx, m dy is given by the surface integral over this region R. Surface integral, this is the C means this boundary. You know, when you find out the line integral is the path integral. Line integral is also known as path integral. You go along the boundary. So it is here line integral over C. When you talk of surface, it is this region. Surface integral over the region R, partial of n with respect to x minus partial of m with respect to y, dx dy, where C is traversed in positive direction. I have also discussed with you what we mean by positive direction. This is okay. Well, I assume here the equations of the region is, our region is bounded by x greater or equal to a, less or equal to b, and y, this is y is greater or equal to f1x. Because when you say this is a curve, this is actually the curve, this curve, y is equal to f1x. When you say greater or equal to y, greater or equal to f1x, that means this part is included and above it. Come here. It is y is equal to f2x. When you say y is less or equal to f2x, that means this part. It encloses this region lying between this and this. Next, if we consider this region, we can draw this here also. This is y greater or equal to c, less or equal to d. This is y axis. Sorry, this is your x axis. As you know, this is your y axis. When your y is greater or equal to c, less or equal to d, the equation of curve, in that case we take x is equal to psi 1 y, x is greater or equal to psi 1, this one, y is, if you want to have the separate figures, you draw for this region, x greater or equal to a, less or equal to b, y greater or equal to f1x, less or equal to f2x, you can have this. I have also given you the OR option here. You can draw this region, this figure for this region. You can have this region when x is greater or equal to psi 1y and less or equal to psi 2y, psi 1y, psi 2, and y is greater or equal to c1 less or equal to y is greater or equal to c less or equal to d. It is this region. I have these two I have combined here, or you can go separately also. Okay, this is the statement of this Green's theorem. What Green's theorem gives us, the relation between the line integral and the surface integral, and I have considered the region bounded by this, and we will have now the proof. Proof you will enjoy, very simple. We have the proof. Let us go to the proof of this result. Now you will take a screenshot of all this what is this theorem वगैरह, and this is statement. I will drop it now. I don't need it. Now we will have the proof. Let us have the proof of this theorem. In the proof we write, this is the proof of the result. We write here, suppose we say, let us consider our region R. Let us consider the region R is given by the system of inequalities. It is this inequality. I will first take this. X greater or equal to A, less or equal to B, comma, whenever Y is greater or equal to F1x, less or equal to F2x curve, or it is given by the system Y greater or equal to C, less or equal to D, X greater or equal to psi 1y, because we have used it here F1, psi 1y less or equal to psi 2y. It is this psi 1, this is X psi 1y, X psi 2 is here, psi 2y, greater than psi 2 means this part, less than. If you are getting confused here, come here. This is X is equal to psi 1y, this is X is equal to psi 2y, greater than psi 2 goes this, less than. Why it goes this way? Because it lies between C and D. C and D on the y-axis, because your y is greater or equal to C, less or equal to D. Here it is going up x-axis, down y-axis, because it is lying along x-axis, because x is greater or equal to A, less or equal to B. You will understand this, there is no problem in it. So we consider this region R is given by this, and this R encloses the closed curve. C is R encloses the, so this closed curve C. Well, now we look here. The equation of curves. You have curves here. Consider AEB and AFB are given by, these are given by y is equal to f1x and upper part y is equal to f2x respectively. The lower part AEB is given by y is equal to f1x. The upper part is given by AFC. When these curves close or close, they form the region R. Okay. Now the region R is bounded by closed curve C. You know our right side is surface integral, you know, or partial derivative of n with respect to x minus partial of m with respect to y dx dy. We have to prove this is the line. We will start from the right side. From right hand side of the result, the result that we have to prove, we consider this part. We consider the surface integral. We find the value, in other words, we consider double integral or surface integral over R, partial derivative of m with respect to y, dx dy. Again, I have taken also this region here, y greater or equal to c, less or equal to d. You don't need to write similarly, because in some cases, in some books, in some proofs, you will see they say that for if they find del m by del y and say similarly for this, or find this similarly for, but we'll find out both, because we have given the region along x-axis and along y-axis. So we take both the things. Let us see what is this region. I will rub it. You see how we find out it. This is your surface integral over R, partial derivative of m with respect to y, dx dy. We write it. Now look to the curve. It is x is running from, x is from a to b, double integral, and y is going from, y is from f1 x to f2 x. Partial of y, we will take this part here first, because it is with respect to y derivative. I will take this one. You just see what I am doing. M with respect to y dx. Because this is the function of, m is the function of x and y, it is partial derivative is present with respect to y. You are integrating this part with respect to y, when it is itself the partial derivative of m with respect to y. So integral and differential, these are what? Reciprocals of each other. In your previous, they are reciprocals of each other. So integral, this is the integral with respect to y, it is the differential with respect to y. What will you get? You get, this is out, integral x to a, it will be here now simply m, it is all m, but it is a function of x, y. We write it, y going from f1 x to f2 x. Please understand it. This is partial derivative of m with respect to y. It is a function. You have to integrate this function with respect to y, but it is itself the derivative of y. So it is reciprocal of each other. You get only mxy. Now give the limit. These limits are for y. You get here, this is integral a to b m. Give the upper limit. It is for y, x, f2x. Do you follow? Minus m x f1x. Dx is there. Dx I have not written here. Dx is here present. Dx. It is dx. Now with respect to derivative y, we have calculated it given this definite integral for y running from f1x to f2x. So it is x. When we give the value to y, it comes to this. Now we will this distribute the integral. So my surface integral, double integral over R, region R, partial of m with respect to y, dx dy comes out to be, what is it now? It is integral a to b m x times f2x dx, then minus integral a to b m x times f1x, this one, dx. Name this equation number 1. Now just look now. Have a look to this. Now we have right hand side of first is what? It is a right hand side the first integral this. The first integral is this. It is the line integral from A to B along the curve y is equal to f to x. Look there, A to B, this is your AB, it goes A to B along y is equal to f to x, so it goes this way. It is not a positive path. It is not a positive path. If we have to integrate this from, if we have to integrate this curve y is equal to f to x along positive path, we must go from B to A. A to B is not a positive path. Do you follow me? Now look here. This second integral. Second integral of right hand side is what? Line integral from A to B along y is equal to f1x. This is your y is equal to f1x. When you want to integrate it, you have to integrate from A to B. It is a closed path. This is okay, but this is not okay. We have to change it because we want positive path. Okay. So when you have to integrate this, you have to go from B to A, not from A to B. Do you follow me? Let us write here something so that you will understand. I will mention here the right hand side integral or we may use shortcut. I will write on right hand side of first, that is this, the first integral because it consists of two integrals. The first integral of this is line integral from A to B. It is from A to B along the curve. Along the curve is this, y is equal to f to x, and second, that means this is a line integral from again A to B along the curve y is equal to f1x. Along the curve y is equal to f1x. This is the line integral along the curve y is equal to f to x, but it should go from B to A. It is A to B, it is not a positive. When you integrate this y is equal to f to x, we have to integrate it positive direction from B to A. Then it becomes a closed path. So therefore we write, in order to have a closed path, in order to have the closed path in positive direction, we must evaluate first integral from B to A along y is equal to f to x. So we must evaluate this from not A to B, from B to A. Then we will have a positive path. Therefore, what we do here, if it is not visible, I will go here. So I will write it now. It is my double integral over the region R, partial of m with respect to y, dx dy is equal to, now when we change here integral, it will be minus A to B m x f to x dx, then minus integral. This will be not now A to B, this is now, sorry, this will be your B to A. Instead of it is B to A, it is A to B, okay. This is m x f1x dx. Now look what is this. You can write it minus now. I will write first this integral. A to B m x f1x, then plus B to A mx f2x dx is here, dx. Now look, you are integrating. This is the integral of this y is equal to f1x. This is your y is equal to f1x from a to b. A to b. Then integral of this y is equal to f2x. Y is equal along this y is equal to b to a. It is now b to a. It is a closed path. Now you are integrating along the boundary. Along the path. This is the line integral. You can write this also this in this way, minus a to b m xy dx plus b to a m xy dx because in both the cases you have y is equal to f1x and upper case is y is equal to f2x. You can replace here y by x. Now what is this? Now it is a line integral. It is the closed boundary C. So it is a line integral, closed line integral, closed curve, this along the curve C, because curve C comes under A to B, B to A. This you will write m xy dx. M xy dx. So we have this line integral or partial derivative of m with respect to y dx dy is this. Or we can write it, take minus here, we can write it minus times surface integral or partial derivative of m with respect to y dx dy is equal to line integral over the closed curve C. It is your m dx. So I need it later on. I will name it equation alpha. Let this be equation alpha. When you have understood this, you have understood the theorem. Now we have second part. Second part you can write similarly also, but I will not take similarly because I have chosen another region. When my x is greater, x is greater or equal to psi 1y, less or equal to psi 2y, and y is greater or equal to c, less or equal to d. I have mentioned this also in this figure in the top. I have also mentioned it there. Now I will write here similarly what we did here. Similarly, we come from this curve represent this EAB, the equations of curves EAB. Here I saw also given it is EAB. This is your EAF, sorry, it is F here, it is B. Equation of curves EAF. I am coming this way now because I go under this EAB, this curve, and EAB and EBF. This part. For this region we took this part and this part. Now for this region we take this part and this part, or we can draw the figure separately. Similarly, the equation of the curve EAF and EBF be given by x is equal to psi 1y and x is equal to psi 2y respectively. So that region R is bounded by closed curve C. Now we calculate now surface integral or partial derivative of n with respect to x dx dy. Similar lines we will go. it is integral here y limit y from c to d, then integral x from x is psi 1 y, it is psi 2 y. I will also take here x partial derivative of n with respect to x dx. I will take y out because for y I have the constant limit, and for x it is involved with partial derivative of n with respect to x. By previous result, it is actually nxy, function of xy, which is whose derivative is dou n by dou x. It is integrated with respect to x, so it is simply n. It is c to d, and it comes out to be now only n xy. Limit is from x going from psi 1 y to psi 2 y. It is your dy. Let us calculate this as we did previously. Let us see what happens. This is your surface integral or partial derivative of n with respect to x d. This is your c to d. Give the upper limit. It is for x. It is n. X is psi 2. It is psi 2 y, comma y minus n psi 1 y, comma y, comma y, then it is your dy. This gives you integral c to d and psi 2 y, comma y, dy minus integral c to d and psi 1 y, comma y, dy. This is your second. Now look here. Right hand side of second. Look, the first integral is the line integral from c to d along the curve x is equal to psi 2 y. Look at psi 2 y. This is your psi 2 y. This part is your x is equal to psi 2 y. When you go from this c to d, it is like this. It is positive part. It is positive part. You are going this way. This way. It is a positive part. C to D. C to D is positive part. Now look here. Psi 1 y. This is your psi 1 y. When you want the positive part for this, how should you go? You should go like this. It should go like this. But he says C to D. It should not be C to D, then it should be D to C. This integral should be D to C. If you integrate this part, psi 1 y, x is equal to psi 1 y, positive part, you should integrate it from D to C in line integral, positive part of the line integral. So I will write also on a right hand side of second integral. First means this is line integral. It is line integral from C to D along curve x is equal to psi 2 y. Look at psi 2 y, where it is. If we want this positive path, it goes from C to D this way. It is okay. And second integral is again C to D along what x is equal to psi 1 y. But second, for psi 1 y, we must integrate like this. This is the curve. If we want to find out the positive integral of this positive part, it should be D to C. So to have positive part, for positive path, we must evaluate second integral from what? From not C to D, D to C. D to C we should go. So according to this, what is this? I will rub it. So I should go this way now. This is your, for positive part, it is okay. C to D and psi to Y, Y, dy. This should be now not C to D, it will be now D to C. When you change it will be plus now, because you are changing the integral. It is n psi 1y, y, dy. Now your x is in both cases, x is psi 1y, x is psi 2y. You can write it in this way, integral C to D, it is n xy dy, then plus D to C and xy dy. It is the line integral. It covers whole the curve. It makes the boundary fully closed. So this is the line integral over the closed curve C, and you may write n xy dy, or you may write this line integral curve n dy. So what we have got here? We have got this. It is surface integral over R, partial derivative of n with respect to x, dx dy. It is line integral over the closed curve C and dy. This is your beta. This is your beta function. This is your beta. Do you follow me? This is beta. It is not a lengthy theorem. I have given you in first the explanation, and even you don't know, if you have this theorem in the examination, if you have state and prove in the examination, then you have to do it. If you have application, then you only read it, then do some application. No need of this. I have already told you what is the application. We find out the line integral, surface integral in terms of line integral, or we can evaluate line integral in terms of surface integral. There is a relation between line and surface integral. You can take only this part, this, or you can take these two theorems. These two, I mean, figures. You see what we do now. Now we are adding alpha and beta, adding alpha and beta. When you add alpha and beta, I will write it minus surface integral R del m by del y dx dy plus R del x dx dy is equal to line integral C m dx, line integral over C and dy. Now when you combine the two, it implies dx dy it is m dx plus n dy. So we have proved the theorem. This implies what we have proved. We have proved that line integral over the closed curve C, where when m and n are both functions of x, m dx plus n dy can be expressed in terms of the surface integral over that region R. Region R is enclosed by the closed curve C, as we state in this statement. It is partial derivative of n with respect to x minus partial derivative of n with respect to y. Here I have taken, or you can take here, you can write here also. No need of this, you can write here in this way. This is your minus del m by del x dx dy. Okay. It is your del n by del x. minus del m by del y dx dx. This proves your Green's theorem in full. This is the Green's theorem. It is a very important theorem. I will write next lecture on this Green's theorem. I will give you what is the generalization of this when we write this Green's theorem in space. Green's theorem it is xy plane. When we write in space, what does this represent? That is the Gauss divergence theorem. I will give you this description later on. I hope you have understood it. Thank you very much, and wait for the next lecture. Thank you very much.